Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll be starting the lecture 11 of linear algebra chapter. So we're almost at the end of this eigenvectors and eigenvalues topic. After this we'll start a new topic, that is a vector space, okay, about vectors, vector span, vector space, okay, and after that this chapter will end. So in this lecture basically we'll do questions on eigenvalues and eigenvectors and few miscellaneous topics which we missed out on. Okay, before starting this lecture I want to go to the lecture 10 and quickly just give you a quick recap of everything. Also I added one more point about the definition of eigenvectors. So I skipped this point previously actually. So the definition of eigenvectors here, right? So I told you like eigenvector simply like it's like just like a scaling factor, right? If I multiply eigenvector with its a matrix, then I will get the same eigenvector, just its scaled version. So in control systems or in signal systems, if you have already studied, you might know like the system has this eigenvalues, right? So there what happens if I give some input x, right? Let's say this is the input vector. This is the input vector. Okay, if I give some input vector x, then what do I get at the output? I get some output vector which is b. Okay, output vector which is b. Output vector which is b. So now what this linear system does is, this linear system gives the same output vector, just a scaled version. Okay, so this linear system has its matrix or characteristics matrix like this a, and if I give it some input vector, the output vector that I get is same as input vector, just a scaled version of it. That is what this like the second diagram is showing, right? I'm giving it some input vector. Okay, giving it some input vector, or you can say giving it some input signal. I'm just getting a scaled version of the just hold a second, scale version of the output signal. Now in signal system, what you should say is like if you give it some sinusoid input, you get same sinusoid input of same frequency remains same, but the phase and magnitude just changes. Basically it gets scaled. So here also phase and magnitude changes. So this is the output vector. Okay, you can see the input vector and output vector, just hold on a second, the input vector and the output vector are same, just they are scaled version. Okay, so let's read this statement. Non-zero vectors, but it has to be non-zero, because if I am giving zero input, that doesn't make any sense. Okay, anyways I will get no output, right? That doesn't make any sense. That's why it has to be non-zero input. Non-zero vectors which are proportional to the input vector after applying to a linear system are known as eigenvectors. So if I apply it to a linear system and I apply a non-zero vector and I get the output as the same non-zero vector which is proportional to the non-zero vector, then that vector, input vector, is known as the eigenvector of that linear system. Okay, this is a definition of the eigenvectors. Another definition. Okay, so basically saying the same thing but in different intuitive approach. So this might be helpful in signal system or in control systems. Now the proportionality constant is known as eigenvalue. So here whatever the proportionality constant is, this is known as the eigenvalue of the those input, right? Particular input, those system eigenvalues of system are this proportionality constant. Okay, so this is another definition. So then I told you, right, these are same only. I explained like a n cross n matrix will have n eigenvalues. Few of them might be repeated, few of them might be distinct. It doesn't matter. If all of them are distinct, then definitely I will get distinct eigenvalues. If few of them are repeated, then it will depend on the rank of a minus lambda I, right? Or a minus lambda 1 I, whichever eigenvalue is repeated. So we already did all those things. We already have done more questions over here. Okay, how to calculate eigenvalues and like this, right? How to calculate, like for triangular matrix we like studied a lot of properties, and then we basically went on to do few questions. Okay, and then also we studied about the this thing, right? Cayley-Hamilton theorem. We also studied about this. Okay, so yeah, this is the case. Now let's start today's class. Basically, so we studied about all these matrices. I will go again over this. So in today's class we'll do questions obviously. So let's first read this question. We have to find the eigenvectors of the following matrix. So for the following matrix we have to find the eigenvectors. So in the previous class I ended here, right? I told you The eigenvectors may be different, okay, may be linearly independent, but the eigenvalues can be same. The scaling factor can be same. So with this example, I will try to prove exactly the same. Okay, so let's do the first question. We have to find the eigenvectors of the following matrices. Okay, so basically the first I will do a bit brief. Okay, and from next on I will go fast. So basically I have to first find the eigenvalues. So what are the eigenvalues? This is a diagonal matrix. The eigenvalues are 3, 3. Okay, eigenvalues are 3, 3. Even like if you don't want to do the characteristic equation, this is minus 6 trace of a plus 9 equals to 0. So this will be simply lambda minus 3. Oh no, this one over here. Lambda minus 3 whole square equals to 3, right? So lambda equals to 3, 3. So I have two eigenvalues obviously, and two of them are repeated in this case. Now how to solve this? So basically what you can do, you can solve this using the method 1. What is the method 1? Method 1 is basically this equation, right? A minus lambda I into x equals to 0. So a minus lambda into x equals to 0. So if a minus lambda into x equals to 0, then what does this mean? This means a is what? A is 3, okay, 0, 0, and we have to subtract lambda, right? So this is basically we're subtracting 3 on the diagonal elements, and they are becoming all 0, and here I have x1, x2 equals to 0, 0, right? Now what do you observe here? What is my nullity? Nullity of this a minus 3i, what is the nullity? Nullity is basically rank is what? Rank is 0 because all zeros are there. Rank now nullity is number of rows or columns minus nullity in this case, because this is a square matrix. So it is 2 minus 0, which is 2. Okay, so 2 nullity means I will have 2 free variables. Okay, or from here also you can understand that this is 0 times x1 plus 0 times x2 equals to 0. So and the second equation is saying the same thing. So I can choose x1 and x2 anything. X1 and x2 can be anything. Okay, x1 anything. Okay, so this is the case. So this will be so basically my eigenvector x1 will be alpha 1 plus alpha 2, right? Alpha 1, alpha 2, x1, x2, and I can write this like this. Alpha, basically I'm choosing, let me write this properly actually. And basically x1 and x2, and what will this become? So this will become what do I say? So I can assume that x1, x2 are free variables, right? I can assume x1 as alpha 1, x2 as alpha 2. Okay, so I don't have to do it again because 3 is only the eigenvalue, so I will get this. Okay, so what I can do, method 2, what I can do, let me write the eigenvector later. So method 2, what I can do, simply what we know ax equals to lambda x. So again we will use this equation. Basically both are saying the same thing, but still, so if you prefer this method you can use this, if you prefer that method you can use that. This is x1, x2, x1, x2 equals to 3 x1, x2. So basically this will become 3x1 equals to 3x1, which is always true, Then this is 3x2 equals to 3x2. this is also always true, right? Because if x2 is not equal to 0, 3 is equal to 3, always true. Okay, always true. Or if x2 is 0, also that is also 0 equals to 0, right? So I'm free to choose x2 and x1 anything. I'm free to choose x1 or x2 anything. So like this also you can solve, or like the previous method also you can solve, whichever is suitable. Like you can find the rank, right? You can find the rank and the nullity, and from there you can understand how many free variables are there. It will be easier for you using the first method. So many people prefer the first method. So now let me write the eigenvectors basically. So x is simply alpha 1, alpha 2. Okay, so this is equals to, now what I can write this as alpha 1 0 plus alpha 2, not alpha 2, sorry, 0 alpha 2. I can write like this, right? Now what I can do, I can take alpha 1 from this common, this is 1 comma 0, plus alpha 2 I can take common, this is 0 comma 1. Now these are independent, right? Because I have two variables. Okay, if I multiply anything with this, this will never become this, right? So these are two linearly independent. Okay, so yeah, these are two linearly independent. Now basically that this is what I wanted to prove, right? That even though your eigenvalues are same, but you are getting two different eigenvectors. That is also possible. Like, what are the eigenvectors here? This and this, right? This is, let's name this as v1, and let's name this as v2. Okay, these are the two eigenvectors that we are getting. Now let's go to the second question, that is a B question, right? So we have to find the eigenvector for this also. So again, right, this is a upper triangular matrix. So basically how you can solve, if it is an upper triangular matrix, right, its eigenvalues will be simply the diagonal elements. So lambda equals to 1, 4, 9, one, 4, 9. Okay, so eigenvalues are 1, 4, 9. Again, you can use that method, right? Now corresponding to lambda equals to 1, what will be my eigenvector, right? What will be my eigenvector? Simply you first write the matrix. So this first element will be 0, this will be 3, 5. I'm doing a minus lambda I. Okay, a minus lambda I into x equals to 0. Equals to x1, x2, x3. Equals to 0, right? Null matrix. So basically what, like, how many free variables are we getting? So if I observe this carefully, if I how many pivot columns we have? We have 1 and we have 2, right? So we have 2 pivot columns. There will be 1 free variable. We can understand the nullity is 1. Okay, you can do it many ways. You can again subtract this, right? You will get 0, 0 over here. This element I can subtract this, I will get row of 0. Whatever you choose. Okay, you will be able to find out that here rank is how much? Rank is 2, because I will have 2 linearly independent columns. Rank is 2. Okay, you find out. Okay, you can just see from here. Now nullity will be 3, order minus rank. 3 minus 2 is 1. So nullity is 1. Hence there will be one free variable. What will be that free variable? We'll see. So let me write the last equation, that is 8x3 equals to 0. So x3 equals to 0. Okay, next 3x2 plus 5x3. 3x2 plus 5x3 equals to 0. Okay, 3x2 plus 5x3 equals to 0. Next 2x1 plus 3x2 equals to 0. Now, okay, this is x3, right? Just hold on a second. Yeah, this is x3. So x1, there is no relation for, so this is also not x1, sorry, this is also 0. So there is no relation for x1. So obviously x1 will be free variable in this case. So basically x2 is 0, so x3 is 0, so x2 will also be 0, and x1 is free variable because there is, like, I can pick x1 anything, right? I can pick x1 anything because x1 doesn't come into this all three equations. So x1 can be alpha 1. So my eigenvector corresponding to 1 is something like this: alpha 1 1 0 0. Okay, now let's go to the second one. So I'll just copy this. Okay, so now let me make lambda equals to 3 or 4, sorry, lambda equals to 4. So if I make lambda equals to 4, what will this become? Lambda equals to 4. So if I make lambda equals to 4, what does it become? It becomes 1. This is minus 3. This is 0. This is 5. And okay, so now again we're observing, right? We're observing that these two are dependent. So again I will have 1, like rank will be 2 again, my nullity will be 1 again, I will have one free variable. Now what will be that free variable? So this time, right, I can see that 5x3 equals to 0. 5x3 equals to 0, hence x3 will be 0. Fine. Now here minus 3 x1 plus 2 x2, and x3 is anyway 0. I'm not writing x3 equals to 0. So x1 equals to 2 by 3 x2. You can choose anything. Okay, you can choose anything. Like you can choose x2 equals to 3 by 2 x1, whatever you want to choose. So so I'm choosing x1. So x2 I can make free variable. Either one is fine. x2 I'm making free variable, which is alpha 2. Okay, so what will be my eigenvector? So x2, so it will be simply alpha 2, and this is basically x1. So this is 2 by 3, this is 1, this is 0. 2 by 3 1 0. Okay, 2 by 3 1 0. So yeah, this is the case for x2. So let's now find for x3. Okay, so we'll again copy and paste, basically copy and paste. Okay, for lambda equals to 9 this time. So for lambda equals to 9, what will happen basically? Let me just delete this. Lambda equals to 9 is minus 8 minus 5. Minus 8 minus 5. Minus 8 minus 5 and 0. Minus 8 minus 1 0. Okay, so basically again what we see, this is a whole rows of zeros. Again the rank will be 2. Again nullity will be 1. Let me solve the equations. So at the end, like let me solve the second one. So minus 5x2 equals to plus 5x2 equals to plus 5x3 equals to 0. So x2 equals to x3. Okay. Now the first equation, so this is x1 plus 2x2 plus 3x3 equals to 0. Now x2 equals to x3, right? X2 equals to x3. So what I can do, I can put over here, like I can choose x3 anything, right? I can choose x3 as alpha 3. Okay. Now if I choose x3 as alpha 3, what will this become? So this will be 5 alpha 3 by 8. x1 will be equals to 5 alpha 3 by 8. x1 will be equals to 5 alpha 3 by 8. Okay. So yeah, this is basically what we get. So our this x3 solution vector, right? x3 solution vector will be five by 8 1 1. Okay, 5 by 8. Oh, everything is recording, right? Just get tensed sometime. Yeah, 5 by 8 1 1, and of course we have alpha 3 at the start. Okay, so basically these are the three vectors we get, right? And for what do we observe? For three distinct eigenvalues, here we have three distinct eigenvalues. I am getting three vectors. Okay, three vectors. Now again, this will do the same example again, that for two same eigenvector values, am I getting the same eigenvector or not? Okay, so let's see that. Okay, again the second example of the thing that we discussed in the previous lecture. Okay, again this is a UTM, right? This is upper triangular matrix. Now if it is a upper triangular matrix, lambda equals to 1 comma 4 comma 4. So lambda is equals to 1 comma 4 comma 4. So basically what you can do, what will be the eigenvectors? So first I will do lambda equals to 1. So for lambda equals to 1, a minus lambda, right? So this is 0 2 3 3 5 0 3 0 0. Equals to x1 x2 x3 equals to 0 0 0, right? So what will this become? So this is 3x3 equals to 0. So x3 equals to 0, that is for sure. Now x2 is also equals to 0 because we're using the second row. So 3x2 into 5x3 equals to 0. Now what about my last one? So last one is again like saying the same thing only. Okay, so we don't have any x1. So x1 can be a free variable. x1 I can choose as alpha 1. So again, what is the eigenvalue that I get? What is the eigenvalue that I get? I get x1 equals to alpha 1 1 0 0. Okay, 1 0 0. Now what about my lambda 2? So again, right, I will copy the same thing. Lambda 2 equals to 4. So for 4, how many values I get? So there, right, what was the nullity? Here what was the nullity? Here nullity was 1. Okay, hence I got one independent eigenvector. Okay, here in this case, everywhere, right, everywhere I got nullity as 1. Everywhere I got nullity as 1, so I got one independent eigenvector. Here what was the nullity? Here what was the nullity? If you remember carefully, it was going like 0 0, right? Nullity, if you see, nullity is 2. So I will get two independent eigenvector. This has also been derived in the previous lecture, that whatever the nullity is, whatever the nullity is equals to, that many number of linearly independent eigenvectors I will get. Okay, that many linearly independent eigenvectors I will get, right? So okay, where did it go? Yeah, so here what is the nullity? Nullity is 1. So if nullity is 1, so my eigenvector will be only a single one. I'm talking about the previous lambda. Now this lambda, what we can see is, let me just rearrange the equations. So I'm subtracting 4. So if I am subtracting 4, this will be minus 3. this will be 0, this will be 0. Okay, so this is all zeros, right? This is all zeros equal to 0. So x3 can be anything, x3 can be anything alpha 3. Okay, now again, right, again we don't have x2, we have x3. 5 times x3 equals to 0. Okay, so just hold a second. Yeah, 5 times x3 equals to 0. Okay, so x, am I doing this correct? This is 0. Okay, here x3 can be anything. Okay, but here in the second equation x3 cannot be anything, so x3 has to be equals to 0, right, for the second, due to the second row. So I'm multiplying 5 times x3 equal to 0, so x3 has to be equal to 0. So x3 has been fixed. Now what about x2? So let's solve the first row. So if I solve the first row, this is minus 3x1 plus 2x2 plus 3x3 equals to 0. Now x3 is 0, so x1 equals to where did it go? X1 equals to 3x1 divided by 2, right? Okay, I made a mistake. No, 3x1 divided by 2. Okay, so here sorry, what was okay, so basically I can choose my x1 as alpha 1. Alpha 1 has already been chosen. I can choose my x1 as alpha hold on a second, am I doing this? Yeah, alpha 2, right? So my eigenvector x2 here will be simply, I can take common alpha 2. If I take common alpha 2, what will this become? This will be 3 by 2, and this will be obviously 1. Okay, what am I naming? Sorry, x1 as I'm taking x1 as alpha 2, so this will be 1 only, and this will be 3 by 2, and this will be 0. Okay, here what do you see? We get only one independent eigen vector, right? Okay, this is depending on alpha 2 itself. So why? Because what is the nullity? Here this is row of 0, but can I make this 0? No, I cannot make this 0. Okay, that's why I don't have 2 rows of 0, I have only 1 rows of 0. So nullity in this case, nullity is 1. So it all depends on nullity of the A minus lambda I matrix. It doesn't depend that whether my eigenvalues are repeated, I will get independent eigenvectors, or I may get same eigenvectors, right? It all depends on the nullity of A minus lambda I. In this case, A minus 4A, nullity was this number of columns or rows minus rank of A minus 4I, which is 1 in this case, sorry, which is 2 in this case. Okay, so we get one linearly independent eigenvector, right? So yeah, this is basically about the examples, what I wanted to say with through the examples, how many independent eigenvectors I am getting. So I should write here one linearly independent eigenvector. Here I can write in the first case, right, where my nullity was 2. In this case, where nullity was 2, I can write that I will get 2 linearly independent eigenvectors. Okay, 2 linearly independent eigenvectors. So let's now go to the next question. So what is this next question telling us? So we have been given a v vector, okay, which is an eigenvector of the matrix A, and we have to calculate the value of x. So how do you proceed in these types of questions? So what you can do, you can simply put this vector in the simple equation, right, of whatever condition there was for a vector to be eigenvector of a particular matrix. What was that condition? That condition was Ax should be equals to lambda times x. Now you might say, sir, we don't know what is lambda here, and that is fine, because with other equations you will be able to find out lambda. What I am trying to say, I will explain. Let me just write the matrices. So here this is A, right? I will just copy and paste this. Okay, then I will copy and paste the vector. Questions also come out. Equals to Ax equal to lambda x. So this is lambda, and lambda x is this itself, right? -1, -2 and 1. Okay, so this becomes 4 times -1 -4, 2 times -2, so -4 -2, 2 times -2 into 2 times 2, so this is +2, which is equals to minus lambda, right, on the right hand side of the first row. So lambda equals to 4. So lambda equals to 4 I got. Now where is x? I will target my x, right? X is in the third row, so I will solve the third row right now. So third row I will solve. So this will be just let me check everything is recording, right? Everything is recording. This is recording. Yeah, this is recording. Okay. This is minus x plus 8 plus 10 equals to lambda. So x is equals to 18 minus 4, which is 14. So x is equals to 14 in this case. So our answer will be 14, right? Answer will be 14. This is the answer. Let me use another color. Pretty simple question, right? These type of simple question comes in Eigenvectors, Eigenvalues chapter. Okay, let's solve the second next question. Okay, where did it go? Okay, what happened? Okay, yeah, this is the next question, right? So here we have to calculate a plus b if this A matrix has the eigenvector as 1a and b1. So what you can do, you can find the eigenvectors, from there you can solve, or you can directly put this value in this equation, from there also you can solve. So these has two methods. Let's do it in the first method. First we'll find the eigenvalues. So what are my eigenvalues? So my eigenvalues are this, right? So basically I can use the characteristic equation, which is lambda square minus 6 lambda, and this is trace plus determinant of this matrix. This is 8 minus 15, 8 minus 15, which is -7. Okay, so lambda square 8 minus 15. So if I may write this one, this can be like can I factorize this? So this will be something like this, lambda minus 7 into lambda plus 1, right? I will get the same thing back again. So lambda equals to 7, lambda equals to -1. Okay, so basically now you can find the eigenvector corresponding to lambda equals to 7. So this is a minus lambda I, so lambda minus 7, this is -5, this is 5, this is 3, and this is I am subtracting 7 from 4, 7 from 4, I am getting -3, and this is, so this is basically null, rank is 1 over here, so nullity will be 1 also. So basically x1 equals to x2 I am getting, so I can choose x1 as alpha 1, and my eigenvector will be simply x1 equals to x2, right? So alpha 1 into 1 comma 1, right? So this is what my x1 is looking like. Okay, now let's solve corresponding to lambda equals to -1. So for lambda equals to -1, a minus lambda I, what will it become? So simply I am adding 1, right? I am adding 1 with the diagonal elements. This will be 3, 5. This is also 3, and this is x1 x2 equals to 0, 0. x1 x2 equals to 0, 0, right? So 0, 0. So now this one becomes basically 3x1 plus 5x2 equals to 0. So x1 I can write as -5/3 x2. Okay, x1 is equals to -5/3 x2. So basically I can choose, like, there will be one free variable, nullity is 1, so x2 I can choose as alpha 2. Okay, so x1 will be -5/3 alpha 1. Okay, so this one basically will become where is it? So our second solution vector will become alpha 2, I can take common, this one will be -5/3, and this one will be 1, -5/3 and 1. Okay, so xt is alpha 2 into -5/3, 1, right? So yeah, this is the vectors. So what was the question? The question was that one of my eigenvalue is 1 comma a. So where is 1 in at the above? So this also can be 1, right? This also can be 1, but let's assume this one. So as we are seeing, we have 1 above. If I choose alpha 1 as 1, so if I choose alpha 1 equals to alpha 2 equals to 1, then my eigenvectors will be 1 comma 1 and minus 5 by 3 comma 1. So simply my a plus b is this, right? This is a, I believe, and this is b, I believe. Okay, a and b. So yeah, these are the a and b, right? A and b. So basically a plus b will be what? A plus b will be minus 2 by 3. Okay, a plus b is minus 2 by 3. So this is the answer to this question. Okay, so let's solve another question. We have to calculate the product of eigenvalues. So do you remember the property? Mostly in eigenvalues chapter, right, mostly the properties will get used. If you have to find the eigenvalues, you have to use some other property, right? It's very important. That's why you have to quickly revise the properties. So if they are talking about the product, from product I remember, yes, there was one property that product of eigenvalues of any matrix is equal to the determinant of that matrix. So this is the first thing that should click in your mind. So product, they are asking, so product of eigenvalues, right, product of eigenvalues lambda I should be equals to basically determinant of a. Okay, so if it is equal to determinant of a, that means we have to find determinant of a. How will I find determinant of a? Through this equation. So either what you can do the a inverse, right, then find this matrix, then you can find the determinant. Or if I take the determinant of this whole equation, right, so this I can assume as b, this I can assume as b, this I can assume as b, and this I can assume as c. Okay, so basically if you observe carefully one thing, okay, are there any relation between b and c? Mostly if this type of question comes, right, there must be any relation between b and c. They want to use they want you to use that relationship. Okay, again, relationship comes up every time. So here what I observe, like this is, I know this is difficult to observe, is that I know this because I framed this question, but if you try to observe that this 4 is here, okay, now this 6 is on here, right? So I'm understanding this 4 and 6 are on the second row, that is fine, but this 6 was at the third column, but it is in the second column. So is there any other same relation? So this 3 is in the third column, it's in the second column. So if whatever is in third column, it is coming in the second column. This 9 minus 9 was in the third column, it's coming in the second column. Okay, so columns must have been interchanged. Okay, so columns has been interchanged, fine. Now rows, so this 5, right, was in the third row, it's in the second row. This 4 was in the third row, second row. 6 was in the third row, second row. So these has already been interchanged. This 7 was in the second row, third row. Okay, now minus 9, second row, third row. So basically the two rows R2 and R3 has been interchanged. So basically from B to C, what has happened? From B to C, R2 and R3 has been interchanged, and C2 and C3 has been interchanged. R2 and R3 has been interchanged, and C2 and C3 has been interchanged. Okay, so basically if two interchange operations has already happened, so basically this will make, this is negative, right, this will make the determinant as negative b. Now again I am changing the column, so this will be negative of b, which will make it again positive. So overall what I can conclude is that determinant of b is equals to determinant of c, right? So basically I have a times b equals to c. Now I can take the determinant of this whole equation. This will be determinant of a, determinant of b equals to determinant of c. So basically my determinant of a will be equals to determinant of a will be equals to simply 1. Why? Because b and c are getting cancelled, they are same to each other. Obviously the first assumption is that we are, I have framed this question, but I have forgotten to write this assumption that determinant of b is equals to determinant of c cannot be equal to 0, else I won't be able to divide. Okay, else I won't be able to divide. So that is very important. So here I have found out determinant of a, which is basically equals to the product of the eigenvalues. So product of the eigenvalues lambda I equals to 1 itself. So this is the answer of this question. Okay, answer of this question. Okay. Now I don't have time, like you can check that this is non-zero, right? This has to be non-zero. If this is 0, then we are dead. Okay, so this shouldn't be like the determinant should be non-zero. Okay, so let's solve the second question. So x1 and x2 be eigenvectors corresponding to eigenvalues lambda 1 and lambda 2. Just hold on a second, let me check one thing. Okay, this is fine, lambda 1 and lambda 2, right? So yeah, x1 and x2 be eigenvectors corresponding to lambda 1 and lambda 2. Okay, calculate x1 transpose x2. So basically what do you observe over here is this is a symmetrical matrix. This is symmetrical matrix. So this is symmetrical matrix because if you do x transpose, you are getting the same thing again. If you do doing the x transpose, you are getting the same thing again. But this x1 transpose x2 is a familiar thing, right? Is a familiar thing. This is like a orthogonal, like property of orthogonal matrix, right? So either you can do it like the property of orthogonal matrix, or you can do it directly. Okay. So yeah, let's do this first. So basically, just hold on a second. So this, if I find like the I have to find the this x1 x2, right? So basically, first of all, this is a symmetrical matrix. Now I have to find x1 transpose x2. Now I have to find the dot product of these two. Now basically, if you remember correctly, that whenever I find the dot product, right, if they're independent, they will be equal to 0. They will be equal to 0. So basically I have to find the dot product of the eigenvectors, and if they're independent, they will be 0. If they're dependent, they will not be 0. Okay, so that is the main thing. So are the eigenvalues independent over here? If I get distinct eigenvalues, definitely there will be linearly independent eigenvectors. Now if the eigenvectors are linearly independent, then this whole thing will be 0. Okay, let's we have already done this, so let me prove it to you. So yeah, basically let me find the lambda 1 and lambda 2. So basically I can write the characteristics equation lambda square minus 5 lambda plus this 4 minus 9, which is minus 5, right? Minus 5, 4 minus 9 is minus 5. So how can I write this? This will be simply basically what I can say is I'm not finding the lambda 1 lambda 2. What I can say is basically lambda 1 comma lambda 2 is equals to what? Is equals to minus b, which is 5, plus minus b square, which is 25, minus 4ac, which is plus 20, divided by 2. Okay, so this is equals to 2.5 plus minus 45 divided by 4, so it is equals to 10.125, 11.125. So if I multiply this by 4, yeah, I get this, right? I get this. So basically what you are saying, these are distinct eigenvalues, right? These are distinct eigenvalues. So if these are distinct eigenvalues, my vectors will also be linearly independent. Eigenvectors will be linearly independent. Okay, so if they're linearly independent, that means that x1 transport times x2 will be equals to 0. Now what is your homework? Your homework is actually to find, like, put this eigenvalues in the equation and find the eigenvectors and solve. Find eigenvectors. What is the homework? Find eigenvectors and solve. Okay, so this is your homework basically. Okay, so now let's do like one quick thing, shortcut. So basically shortcut for 4 cross 4. So if you have a 4 cross 4 matrix and you want to find the eigenvalues of this matrix, what you can do, you can break this down into particular sections. Okay, but for that few conditions has to satisfy. So you have to find the eigenvalues of this M matrix. So basically whatever the eigenvalue of this 2 cross 2 eigenvalues will be also the eigenvalues of this 4 cross 4 matrix, and whatever the eigenvalues of this 2 cross 2 matrix will also be eigenvalues of this 4 cross 4 matrix. Okay, so basically I can write this like this. This A is an eigenvalue, this this A is a matrix, 2 cross 2 matrix, B is a 2 cross 2 matrix. So here A comma B are 2 cross 2 matrix A comma B are 2 cross 2 matrix. Okay, and this O, right, this is also a 2 cross 2 matrix. It's not simple 0, this is also a 2 cross 2 matrix. 2 cross 2 null matrix. Okay, so yeah, these are null matrices. Okay, so this is A and B. So whatever the eigenvalues of A and B will be, that will be my eigenvalues of this 4 cross 4 overall matrix M, eigenvalues of M. So here I have written it down. So whatever the eigenvalues of this A, B will be also the eigenvalues of M. I should write eigenvalues M will be the separate eigenvalues of A and B. So even if, like, this is what, this is like a diagonal matrix, right? Just saying this is like a diagonal matrix. Okay, so like a diagonal, this is not exactly like, this is not exactly a diagonal matrix, but like a diagonal matrix, you can remember like that. So like diagonal, how you remember, right? You remember like this, like diagonal matrix. Okay, this is like a upper triangular matrix. Oh no, UTM. Like, no, not upper triangle, this is like a lower triangular matrix, LTM, and this is like a upper triangular matrix. Okay, so basically I get this. So all of them will have the same eigenvalues. Okay, same eigenvalues, but it has to be either upper triangle, lower triangle, or like this. Like, it is not exactly like upper triangular, but just I have you are getting the analogy, right? You have two cross two matrices. Okay, and this can be anything, but still the eigenvalues will be separate A and B of this whole M matrix. Okay, so I hope you got the point. So again, like, this was one shortcut I forgot to tell you previously, so we covered that. Now you have to find, like, A is given, okay, and A is equals to -3 -1 2 0, then you have to find A raised to power 4. Okay, so how we can solve? You can solve using the conventional method. Okay, what is the conventional method? Conventional method is you find A square, then you again find A cube, then you again find A raised to power 4. So method 1, you find A square. So A square will be simply this matrix multiplied twice, 2 -1 0 -3 2 -1 0. So this will be equals to 9 and -2. So this is 7. Okay, now this is -3 times 2 -6 and 0, -6, and this is 3 and 0. So this is 3, and this is -2. So this is -2, right? So now this is what my A square is equals to. I want A raised to power 4. So what will be my A raised to power 4 equals to? So A raised to power 4 will be simply, again, if I multiply A square twice, I will get A raised to power 4, right? A square times A square. Okay, if I do this, I will get A raised to power 4. So I will multiply this matrix twice, -6, 3 -2, 7 -6, 3 -2, right? So what do I get over here? So I get, this is 49 into -18. So this will be 31. Okay, now this is -42. I'm multiplying this, -42 plus 12. So this will be -30. Now this is 21 minus 6. 21 minus 6 is 21 minus 6. 21 minus 6 is 15. And this is -18 plus 4. -18 plus 4, which is 14, right? Which is what? -14. -18 plus 4. So this is what my A raised to power 4 is. Let me check the options. 31 minus 30, 15 minus 40. Okay, this is the option, right? So here, like you can see that, yeah, this is pretty easy, okay, just by manually solving. But sometimes what will happen is this method won't work, okay, for higher powers. Let's say you have to calculate a raised to power 10, okay, or a raised to power 20, or a raised to power 400. Then this method won't work, okay. Sometimes this method won't work. So this is manual computation. Okay, so this is manual computation. So now let's solve the second question. Okay, now let's solve the second question. So not a second, so now let's solve using the second method. So now we will use the Cayley-Hamilton theorem. Let me write this, my Cayley-Hamilton theorem. Okay, so basically how you solve it. So basically we have to find the characteristic equation of this one. So characteristic equation is pretty simple. It is simply 2 cross 2, so it will be lambda square minus trace of a, trace is minus 3, it will be plus 3a, 3 lambda plus determinant of a, which is plus 2, so plus 2. Okay, so you just replace lambda with a, okay, replace lambda with a, this will become a square plus 3a. Now this one will become 2i, okay, equals to 0. Now my a square equals to minus 3a plus 2y. Now what I can do, I can simply square on both sides, right? I can simply square on both sides, or I can multiply a square on both sides. I'm doing the same thing, okay, multiply a square on both sides. So if I multiply a square on both sides, this will become plus 3a plus 2i whole square. So this will become 9a square plus 4i plus 6 into 2, which is 12a. Okay, so this will become 12a. So what is a square again? So a square is this, right? A square is this. So I can write my a square as this. So a square is this. If a square is this, then this is equals to a raised to power 4, 9 a square. A square is minus 3a plus 2i plus 2i plus 4i plus 12a. Okay, plus 4i plus 12a. So this becomes basically minus 27a minus 18i plus 4i plus 12a. So this becomes minus 15a and minus 14i. Okay, so this was my a raised to power 4 is. So basically now I can replace a with the actual matrix is minus 15 times what a is minus 3 2 minus 3 2 minus 1 0, and this is 14 1 0 0 1. Okay, so this will be equals to 45 minus 30 15 0 minus, I can write plus over here, this will become minus 14 0 minus 14. Okay, so okay, let me just add another page. So this will become 31, right? This will become 31 and this will become minus 30. I'm getting correct, right? Yeah, minus 30, and this is 15 itself. This is 15 and this is minus 14. So 31 minus 30, 15 minus 14. Yeah, this is exactly what I'm getting. So you might feel that this is more of a task, but slowly what will happen is this will be lesser of a task. Okay, for higher powers. For higher powers, this will be lesser of a task. Either way, okay, you will get your final answer. No worries. So yeah, let's now go to the next question. So again, now this next question is this, that if -1 and -2 are eigenvalues of a square matrix A, then A raised to power 4 is equals to. Now this, right, you try to, like, you have to solve this using options. You have to solve this, eliminate options. So for A, my eigenvalues are what? My eigenvalues are -1, -2. Now for A raised to power 4, A raised to power 4, eigenvalues will be lambda raised to power 4. We already know this, right? They're distinct, so lambda raised to power 4. So this will become 1. This will become 16. Okay, this will become 16. Now this will become 16, then definitely this basically is 1 and 16. So let me put this in this equation, and it should satisfy, right? It should satisfy my A raised to power 4. Okay, so if I put this like, now what I need to do? So if I put this lambda value over here, it should satisfy my this lambda. What do I mean by this? So basically, what are these options telling? What these options are telling, that A raised to power 4 equals to, so I will just use the same next page, and from there we'll understand. So the first option, we'll check the first option. So first, what is the first option telling us? A raised to power 4 equals to, A raised to power 4 equals to -28 A minus 27I. So okay, I made one mistake. So what I can do is, I can simply put my lambda over here. Simply put the lambda. So I can replace A with lambda, right? Replace A with lambda. Okay, I can replace A with lambda. So if I replace A with lambda, what I will get? So this is lambda raised to power 4 equals to -28 lambda minus 27I. Now you put lambda equals to -1 and 2, and check whether these are satisfying or not. So first I will put -1. So if I put -1 over here, this is 1, and this is -1. So this is equals to 1. So if I put -1, this is 1 equals to -28 times -1 minus 27. So this becomes 1. So 1 is equals to 1, which is true. Okay. So now let's now check for the second case. So for lambda equals to lambda equals to -2. So lambda equals to -2, it won't satisfy. So -2 raised to power 4 should be equals to this, right? Should be equals to 28 minus 28 times -2 minus 27. So here what do I see? This is 16, and this is something else. This is like, this is 56 minus 27. So this is 3 and 6, 9, 9, 29. Okay, 30, 29. Okay, so yeah, so which is not equal. So 16 is not equal to 29. So option A is eliminated. Okay, option A is eliminated. So let me check the second option. So if I want to check the second option, option B, right? So here it is, what it is saying. It is saying that A raised to power 4 equals to -15 minus 49. Okay, so if this is -15 minus 49, so now I will replace this with lambda raised to power 4. Right? So this is -1 raised to power 4 equals to -15 so 1 equals to 15 minus 14. Again 1 equals to 1, true, right? 1 is equals to 1, true. Let me check for the second 2, right? So if I want to check for the 2, this will satisfy actually. So lambda equals to -2. So lambda equals to -2, this will be -2 raised to power 4 equals to this is -15. Just hold on a second. -15 times -2 minus 14. So this is 16 equals to 30 minus 14. 16 equals to 16, right? 16 equals to 16, so this is also satisfying. So obviously my option B will be correct. You can check the other options, those will be incorrect only. Okay, so you can solve this question like this using the Cayley-Hamilton theorem. Okay, so let's solve the next question. So next question, what they're telling. So next question, the matrix A 3 cross 3 has its eigenvalues as 1 minus 1 3. Then the trace of this, what will be the trace of this? So basically, what is trace? First of all, what is trace equals to? So trace is equals to sum of the eigenvalues, right? Sum of the eigenvalues, lambda equals to I to n. So you might think, sir, what is the trace of this? The trace of this is 3. 1 minus 1 plus 3, 3. What will be the trace of this? This is a square, right? So this will be trace of a square is 3 square 9. Trace of a is 3. This is 1. This trace of is 2. So this will be 9 plus 3 plus 2. 9 plus 3 plus 2 will be what? 12, 14. So you must say 14. No, you're wrong, right? That it doesn't work like that. So what you have to do, you have to find the eigenvalues of this matrix. So let me name this matrix as B. Let me name this matrix as B. B equals to A square plus A plus I. Now you have to find trace of B, right? So what will be the trace of B? Trace of B will be sum of, this is lambda lambda I B, the eigenvalues of B. Okay, so you have to find the eigenvalues of B. How will you find the eigenvalues? Simply this is A square, right? So you just put the value of lambda here and you will find the eigenvalues of this B. Okay, you put the eigenvalues of A and you will find the eigenvalues of B. Okay, so yeah, this is how you can find. Just hold on a second. What is happening? My pen is not working. So basically, if I put lambda equals to if I put lambda equals to 1, then obviously my what is this lambda B corresponding to this? Lambda A is equals to 1. So lambda B will be 1 plus 1 plus 1, which is equals to 3. Lambda B is 3. Okay, then let me put lambda A equals to minus 1. So lambda is equals to minus 1, then lambda B will be equals to minus 1 if I put it. So this will be minus 1 whole square minus 1 plus 1 also. Okay, plus 1. So again this is 0, this is again 1. Okay, lambda B is again 1. And if I put lambda A equals to 3, so lambda B will be simply equals to 3 square plus 3 plus 1, which is equals to 9, 10, 13. Okay, so 9, 10, 13. So yeah, this is simply equals to so what will be the trace now? What will be the trace? So trace of B will be simply all the sum of the eigenvalues, right? All the sum of the eigenvalues, which is equals to this time 3 plus 1 plus 13, which is equals to 70. So this will be my answer. 17 will be my answer. The trace of this whole thing. Okay, this is how you can solve using the Cayley-Hamilton theorem, which is very easy for you to solve, right? You have to use the property of Cayley-Hamilton theorem. So we have then given this next question where B matrix is given as A cube minus 2A square plus 2A minus 4I, where I is the identity, where I is a 3 cross 3 identity matrix, the determinant of B. So you have to find the determinant of B, right? Okay, so how will you solve this? So A is given like this. So what you can do? You can write A cube over here, then find the value of B in this matrix format and then find the determinant of that. You can do that. But what other thing you can do? You can, like, what is the determinant of B means? So you have to find the determinant of B, right? So determinant of B basically means you have to find what, in terms of eigenvalues, you have to find the product of the eigenvalues. Okay, product of the eigenvalues of lambda B. So what I can do, you can find the eigenvalues of B with the help of A, because you have been given this equation, right? Okay, you have been given this equation and you can use the Cayley-Hamilton theorem, reverse Cayley-Hamilton theorem. So basically you will put A equals lambda and from there you will be able to solve. Okay, so this will be simply like this. So basically I have to find lambda B, right? So what are the eigenvalues of this? So this is this, right? A is a lower triangular matrix. A is a lower triangular matrix. So basically diagonal elements will be my eigenvalues. So what are my diagonal elements? So my eigenvalues are 2, 1, minus 1. 2, 1, minus 1. So if my eigenvalues are 2, 1, minus 1, now I will find corresponding to lambda equals to 2. This is lambda b equals to what? So I will put this equation, right? I will put this will be 2 cube minus 2a square, 2 into 2 square, plus 3 into 2 minus 4. So this is 8 minus 8 plus 6 minus 4 equals to 2 itself, equals to 2. So lambda b is 2. Now lambda a equals to 1. So lambda b equals to 1 cube minus 2 into 1 square plus 3 into 1 minus 4 equals to 1 minus 2, which is minus 1, plus 3 minus 4. So this becomes almost what am I doing something wrong? This is 1, right? Okay, 1 is minus 2, so this is 3 minus 5. Okay, this is minus 2. Now this is, just hold on a second, I'm thinking about something. Am I missing out something again? So this is again corresponding to minus 1. So this is lambda b equals to minus 1 whole cube minus 2 into minus 1 whole square plus 3 into minus 1 minus 4. So this is equals to minus 1. This will be minus 2. This is minus 3. And this is minus 4. So basically this is equals to minus 10 itself. This is equals to minus 10. Okay. So I will have 3 eigenvalues. Now basically my determinant of b will be simply the product of all these 3. Okay. So this is minus 10 into minus 2. Just hold on a second. This is not minus 10 into minus 2. And this is times 2. So this will be equals to 48. So your answer will be 40 to this. Determinant of b will be 40. Okay. So let's go to the next question now. So what is the next question? The next question is like it is talking, we have a matrix which is a 3 cross 3 matrix that has determinant of a minus identity matrix equals to 0. What does this mean? We'll understand this in a bit. Now it is also telling us that if trace of a is 13 and determinant of a is 32, then sum of the squares of the eigenvalues of a. So we have to find the sum of the squares of the eigenvalues of a. This is what we have to find, right? It will have 3 eigenvalues as it is a 3 cross 3 matrix. We have to find this. Now for this basically we have to find, this is the s, let me name this as s. Now for us to find s, we have to find the individual eigenvalues. So how will I find the individual eigenvalues? I know the trace of a means the all sum of the eigenvalues. So I got one equation. Then determinant of a means the product of all the eigenvalues. I got 2 equations, but I have 3 variables and I will need 3 equations, right, to get a unique solution. So here, what is this? What is this telling us? Generally, what is the equation? If you remember correctly, that the determinant of a minus lambda I equals to 0. What does this represent? This represents that my lambda is an eigenvalue. Lambda eigenvalue. Now in this case, it is determinant of a minus 1 into I. So it is given in the question that we have a minus 1 into I equals to 0. That means lambda equals to 1. So one of the eigenvalues is 1. Okay, and let's now solve the other 2 equations. So summation of eigenvalues, lambda 1 plus lambda 2 plus lambda 3. I will assume this as lambda 1. Lambda 1 plus lambda 2 plus lambda 3 equals to what? Trace of a, which is 13. So lambda 1 is 1 plus lambda 2 plus lambda 3 equals to 13. So lambda 2 plus lambda 3 equals to 12. Okay, this is one equation I got. And on the other one, right, other relation whatever is given to us, it is lambda 1 times lambda 1 lambda 2 lambda 3 equals to what? Equals to 32. So lambda 1 is 1 times lambda 2 times lambda 3 is lambda 2 times lambda 3 is 32. Okay, so if this is 32, now how can I say that what is my lambda 1 lambda 2? So an easier solution is, like, if you can observe this, great. Okay, you can, like, I can observe that sum of two numbers should be 12 and product of those two numbers should be 32. So I'm observing what are the different products of two numbers which gets 32. Like I can get 16 times 2. Okay, 16 times 2, but the sum is 18 over there. Now I can, next what is there, like I'm talking about the whichever integers, I'm talking about the integer numbers. Next is 8 times 4. 8 times 4 is 32 and summation is 12. So that is satisfying. So my lambda 1 lambda 2 I can take as 8 and lambda 3 I can take as 4. Now few students might say, sir, we generally tend to get confused in this area. We are not able to guess correctly. Okay, it is taking us a very high amount of time to guess. So whenever you are getting sum of two numbers and product of two numbers, you can form a quadratic equation from that. So you know sum of two numbers, right? So what quadratic equation you can form? Lambda square minus the sum of two numbers, which is in our case minus 12 lambda, plus the product of two numbers, which is in our case 32. Okay, so you form the quadratic equation. From here you can directly use the quadratic formula. What is the quadratic formula? So lambda equals to minus b, which is plus 12 in our case, plus minus b square 144 minus 4ac, which is 128 by 2a. Okay, so this will be 6 plus minus under root, this is how much? This is 2 6. So 136 sorry, I am talking about 2 and 4. So yeah, 134 10. So this is 16 and we have divided by 2. So this is 6 plus minus 4 divided by 2, which is plus minus 2. So this is simply equals to 8 and 4, right? So from here also you can easily find out if you are not able to guess correctly. Okay, this is also another way you can find the solutions of, if we have given sum of two numbers and product of two numbers, directly you can find from here itself. Okay, so 8 and 4. So what have they asked us? They have asked us to find the square of the sum of the squares of the eigenvalues. So if they have asked us to find the sum of the squares of the eigenvalues, so basically it will be lambda s will be equals to 1 square plus 4 square plus 8 square. So this is 1 plus 16 plus 64. So this is equals to 81. So our answer will be 81, C. Okay, option C will be the correct answer in this case. So now let's go to the next question. So what is the next question? So here the eigenvalue of a 2 cross 2 matrix are minus 2 and minus 3. So eigenvalue of a 2 cross 2 matrix are minus 2 and minus 3. Then eigenvalues of a matrix of this. So my new matrix is B equals to x plus I inverse x plus 5i. Okay, x plus I inverse x plus 5i, right? This is my new matrix. Now basically what will be the eigenvalues of this matrix, right? Simply what you can do, you can simply use the Cayley-Hamilton theorem again. So you can put the lambda again. So lambda b will be equals to what? Just hold on a second. Okay, I can keep this in here. So lambda x equals to, for minus 2, what is my lambda b? Simply it is equals to, I can say minus 2 plus 1 inverse minus 2 plus 5. So this is 3 and this is minus 1. So this is minus 3. So I have got one eigenvalue. I have to write down another eigenvalue. So another eigenvalue, lambda x equals to lambda is equals to minus 3. Lambda is equals to minus 3. Okay. Now this is equals to lambda b equals to what? This is minus 3 plus 1 inverse, and this is minus 3. Okay, wait, where did I go? Minus 3 plus 5. So this simply becomes 1 by minus 1 by 2 into 2. So this is simply minus 1. Okay, this is simply minus 1, right? So yeah, this is the answer to this question. So my eigenvalues will be lambda b will be, one will be minus 1, another one will be minus 3. Okay, so these will be my eigenvalues of the new matrix. Okay, so it's just simple. In most cases you will use some property or Cayley-Hamilton theorem mostly. Okay, now this is another question. We have to find the sum of the eigenvalues of matrix A. So what will be the sum of the eigenvalues? So sum of the eigenvalues of this matrix A, right? It will be the trace of A. Okay, trace of this matrix. So here it is given in terms of n. So you can use two methods. You can eliminate the options. You can pick n equals to 2, n equals to 3, and for smaller numbers you are checking the sum of those numbers, that you can do. Okay, so method 1 is eliminate options. I am not doing it. Eliminate options. Okay, and what is method 2? What is method 2? Method 2 is like basics. Okay, basics. What we know trace, basically sum of eigenvalues equals to trace of A. So trace of A in our case is what? In our case 1 into 1 by 2 plus 1 into 2 into 3 plus 1 into 3 into 4. Okay, so now here what you can write? So basically you can write, like, now you have to remember this. So like this thing is I also tend to forget this trick. So what a trick you have to use here is this 1 by 2, right? This 1 by 2 I can write as 1 minus 1 by 2. Now another trick, basically they are giving you two multiples, right? So you have to write them separately. So this is 1 minus 1 by 2. This will be 1 by 2 plus 1 by 2 minus 1 by 3, and you will get exactly this. So this you have to remember these tricks, right? This how conversion, because these type of conversion also come up in aptitude also, some other place also. So you have to remember this. No other option. So if you don't want to remember this, you can directly go with the options. Check with the options, right? So next this will be plus 1 by 3 minus 1 by 4, and this will go on until 1. So here what do you notice here? This is n cross n matrix, and last one is n plus 1, and this is n. So what will happen is this will be minus 1 by n, then plus 1 by n, and minus n plus 1, right? So this will become 1. Everything else will get cancelled basically. If you observe here carefully, this is getting cancelled, this is getting cancelled, this is getting cancelled. So everything else will get cancelled. Only we will be left with this 1 minus n plus 1. Okay, 1 minus n plus 1. So this will be simply n plus 1 minus 1. So this is n divided by n plus 1, n divided by n plus 1. Okay, so yeah, this which option is present over here? Yeah, option B is present over, right? So this will be correct. Okay, so for checking of the options, you have to go with higher numbers also, because few of them will be same only. You have to check for all the options. So that is one thing. So yeah, basically that was it for the questions. If you want more questions, do let me know. I will try to do more questions on eigenvalues and eigenvectors. For me, I think this is enough. And few questions you have to practice also. I try to take as little gate PYQs as possible so that you can practice those by yourselves. Okay, so now let's come to this miscellaneous topic. Okay, the first one is similar matrices. So what is a similar matrices? Basically, matrix A is said to be similar to another matrix of same order if and only if there exists an invertible matrix such that B is equals to P inverse AP. So what is the invertible matrix? It is the similarity matrix. So invertible matrix is the similarity matrix. If there exists a matrix P such that they are related, A and B are related like this. Okay, A and B are related like B is equals to P inverse AP. Okay, B is equals to P inverse AP. Okay, now the transformation of A into P inverse AP is called similarity transformation. The transformation of A into P inverse AP is called similarity transformation. Okay, so this transformation of A to B is called as similarity transformation. So basically this can be written in some other format also. This generally more intuitive way to understand this is basically if I multiply, like if I pre-multiply P on both sides, sorry, not pre, okay, yeah, I can pre-multiply, right? If if I do pre-multiplication, this will be okay. So basically this will be P B equals to AP, right? So if I pre-multiply B, then I will get A times P. Okay, this P will be remained everywhere. So this is basically my similarity transformation. So like if you can't remember this, you can remember this also. PB equals to AP. Okay, and P will obviously change its side. Okay, if here I had P was, then if I multiply P, no, yeah. So this is basically the similarity transformation. Like this is also how you can remember. Okay, now let's read the next point. Similarity matrices have same trace, determinant, and eigenvalues. Eigenvectors may not be same. Okay, so here A and B are similar, right? A and B are similar because there exists a P matrix that can relate it like this. So in this case, the similar matrix will have same eigenvalues, trace, and determinant. How you can understand same eigenvalues? Why same eigenvalues? Because if you put lambda A over here, whatever eigenvalues of this is P inverse, right? And this is P. So these are in product. So this will be 1 by lambda, and this will be lambda, and this will get cancelled. So only this will get remained. So all the eigenvalues of B and A are same. Now if the eigenvalues of B and A are same, that means trace will be same, because trace is simply sum of the eigenvalues. That means determinant will be same, because determinant is basically product of the eigenvalues. Now eigenvectors may change. Eigenvectors of B may change, but eigenvalues will remain same. And as eigenvalues are remaining same, these two properties are also will be also same. Okay, so this is the basics. In short, you have to remember, just have to remember these 3 points, and that's it. Okay, because theoretical question may come up, and sometimes you may have to do something with similarity matrices, and you can do it with this knowledge. Now next is diagonalizable matrix. What do you mean by diagonalizable matrix? So basically a matrix A is said to be diagonalizable if and only if there exists an invertible matrix P. If and only if there exists an invertible matrix P, okay, such that okay, I should not write P over here. This is D. Sorry, M. This is M, not P actually. Such that M inverse A, M equals to D. Okay, so this is also a similarity type of transformation, but this time whatever this matrix I get, this is a diagonal matrix, and here the diagonal elements are all the eigenvalues. Okay, so basically M will be what? M will be modal matrix formed by eigenvectors of A. So I'm applying the similarity transformation again. Okay, and by applying the similarity transformation, my this matrix similarity matrix is the modal matrix. In this case, is the formed by eigenvectors of A. Okay, so and the result after applying the similarity transformation, the result that I will get is the diagonal matrix, and diagonal matrix will have all of its eigenvalues as basically same as A. Basically the eigenvalues will be same, right? This is simply I'm doing the similarity transformation. So eigenvalues need to be same, and as I'm getting diagonal matrix, the eigenvalues will be this only. Okay, so yeah, this is the case. So A of order n cross n is diagonalizable if and only if it has n linearly independent eigenvectors. Why is this the case? Because if linearly dependent eigenvectors, what will happen? Can you understand what will happen if they are linearly dependent eigenvectors? Now where am I using the eigenvectors? I'm using the eigenvectors here in the modal matrix. If I'm using the eigenvectors in the modal matrix, that means if 2 columns rows are dependent, we'll do this in the next question also. You know, right? 2 eigenvectors are dependent. Okay, that means basically 2 rows or columns are dependent. Okay, that means this determinant of M will go to 0. Determinant of M will go to 0. Now if determinant of M is going to 0, that means I don't have any inverse. Inverse does not exist. So hence obviously I won't be able to do this transformation. That's why it won't be diagonalizable. So I hope you got the reason. Okay, so this is one thing, they have to be linearly independent. Now do my eigenvalues also have to be distinct? Eigenvalues may be same. Okay, eigenvalues can be repeated because I just proved it to you this start of this class, that eigenvalues, for repeated eigenvalues I am getting independent eigenvectors. Okay, so this point is very important. Someday gate may pick up on this point, right? This point is very important. Okay, this is very important. So basically this was it for this diagonalizable. Now let's do with one example, and from there we will understand. So here it is asking us to diagonalize the following matrix A. Okay, so to diagonalize the following matrix A, how will you diagonalize? Basically what you will do, basically you have to find the eigenvectors of this, and from there you will form a modal matrix, and you will do the similarity transformation, and from there you will be able to diagonalize. So anyway, the diagonalizable form we know, it will be simply the lambda, right? Lambda. Okay, so generally what the question may come is, you may be given the diagonalizable matrix and the modal matrix. So from here one more important point is, if you are given the diagonalizable matrix, right, so I can pre-multiply with m on both sides. So m will be here, and post multiply with m inverse will be here. Okay, and this will be equals to a. So if this one is equals to a, so m d m inverse, madam inverse, right? You can remember like this, madam inverse. So my A matrix I can write in terms of the diagonal matrix. Basically, if I know the eigenvalues of all the if I know the eigenvalues of A, and if I know the eigenvectors corresponding to those eigenvalues, okay, then I can simply get back my original matrix. So this is also another formula. Okay, this also we can do. Okay, so either way the question may come. So yeah, now here they are asking us to diagonalize. So what we will do? So anyways, you know that after diagonalizing there will be lambda 1, lambda 2, and from the this question itself, it is a lower triangular matrix. So lambda 1 is 1 and lambda 2 is 3. So it is simply the diagonal matrix. So we are expecting something like this. Okay, we are expecting something like this, and let's see if that is correct or not. So basically we already found out the lambdas. So what are the lambda? I will write the characteristic equation. So this I can write the d as, so lambda square minus trace of which is 4 lambda plus 3 equals to 0, plus equal to 0. This is lambda minus 3 into lambda minus 1 equals to 0. So lambda equals to 1 and 3. That is correct only. Okay, so anyways we've already found out that. So yeah, now let's find the eigenvectors. So what are the eigenvectors? So corresponding lambda 1 equals to 1. What is my eigenvector? Simply if I do A minus lambda I, what will happen? This first row will become totally 0. Then this is minus 1, this is 2. Okay, this is x1, this is x2, this is 0 comma 0. Okay, so obviously I'm getting this second relation, that is minus x1 plus 2x2 equals to 0. So x1 equals to 2x2. Now if I assume that alpha not alpha, like the first row is 0 equals to 0, that is always true. So basically x2 I can assume as a free variable. Anyways nullity is 1, so I will have one free variable. I can assume alpha 1. So x1 will be equals to 2 alpha 1. So my eigenvector will be, simply if I do alpha 1, this will be 2 1. Okay, now let's do this second, lambda 2. So lambda 2 equals to 3, right? Lambda 2 equals to 3. So if lambda 2 equals to 3, then I can write here A minus lambda. This is minus 2, this is minus 2, and this is 0. Okay, and this is minus 1, this is 0, this is x1, x2, 0. So this will be simply minus 2 x1 equals to 0. So x1 will be 0, right? And again here also x1 is 0, saying the same thing. So x2 will be some alpha 2. Okay, so basically my eigenvector x2 will be 0. I can write alpha 2 1. Okay, alpha 2 0 1. Okay, so this is my eigenvector basically. So now basically what needs to happen over here? So we got two eigenvectors, right? So I can choose my eigenvector as, like, I can assume alpha 2 equals to 1. So this is 0 1, and I can choose my alpha 1 also equals to 1. This is 2 1. So what will my M matrix? M matrix will be simply equals to 2 1 and 0 1. Okay, and what will be M inverse? M inverse will be simply equals to simply the shortcut, right? I will swap the diagonal elements and make the signs negative of diagonal elements, right? So this will be my basically, okay, I have to swap. I forgot to swap. I told you that I will swap, but I forgot to swap. Okay, so now simply using the transformations, and also don't forget the determinant. Determinant here isn't 1, determinant is 2, right? 2 times 1 minus 0 is 1. Okay, so basically what will happen? So if I do this, this will be like, now I will use the formula, right? Similarity transformation. This is M inverse A M equals to diagonal matrix, right? This was the formula, I believe. Yeah, M inverse M equals to diagonal matrix. So what will happen over here? So M inverse 1 by 2 1 minus 1 0 2. Now whichever eigenvector you write, right, correspond, like whichever eigenvector you write over here, that eigenvalue will come first. We'll see. Okay, now this is what I was mentioning. So here I am getting column matrix, right? This is a column matrix, this is a column, this is a vector, this is a column matrix, this is a column matrix. So these two columns I am putting over here. Now if these are linearly dependent, obviously this determinant will be 0. Obviously I won't be able to find out the inverse. Okay, that's why they can't be linearly dependent, they have to be linearly independent. So this was the case. So what is my A matrix is 1 0 minus 1 0 minus 1 3, and my M is this is, so this is equals to simply 1 0, and this is 0 0, this is minus 1 minus 2 minus 3, this is minus 1, this is 6. Okay, this is 2 1 1, and this will be 1 by 2, it's on outside. So this is 2 0, so this is 2, this is 0 0, this is minus 6 and 6, so this is 0 again, and this is 0 and 6. Okay, so now I can divide by 2, this is 1 0 3, right? So this is what we are expecting, right? This is what we are expecting, 1 0 3. Now why is this 1 over here? Because I wrote the eigenvector, I wrote this eigenvalue, eigenvector here, right? Eigenvector, like this eigenvector is corresponding to this eigenvalue. So this one I wrote in the first column, and the second one was due to this second eigenvalue. So that's why obviously I got the first eigenvalue here corresponding to this first column, and the second eigenvalue corresponding to this second column. So yeah, these also you have to keep in mind. Lambda 1 equals to 1, lambda 2 equals to 3. So yeah, so basically the thing is that like you might say, what is the use of this? There is a use of this obviously, and sometimes you will be given the eigenvectors. Okay, you will be given the eigenvectors, and you have to find the this A matrix. You will be given the eigenvectors, and you will be given the diagonal matrix, and you have to find the original matrix. So that can happen, right? That can happen. So yeah, basically this was it for this lecture. I hope you learned a lot from these questions and all those things. So from the next lecture, we'll start a new topic, that is the eigenvectors, not eigenvectors, sorry, eigenvectors we have just finished. We'll start vector spaces, vector span, and all those things, right? So yeah, I hope you liked this lecture. If you did, do let me know. And like if you want any more thing, if you have any more doubts, you can put it down in the comments or ask in the Telegram group. Thank you for watching, and I will see you in the next video.